We're starting, so please take a seat. I'm kind of hoping that there will be more people actually coming after lunch, or just after lunch. So yeah, the people who are here are the best people, so that you know. And actually, I wanted to introduce Koen. So Koen is from CMU, and he's been doing causality since 2006. I actually discovered recently, and I mean, he doesn't like to say it because he's very humble, but I would like to say that I think, as far as I know at least, he's the first one to do causality and transfer learning together since 2013. Maybe we can argue on that. Maybe Elias has some ideas. We never know. But, I mean, he's clearly very good, and I think this talk will be very interesting to all of us. Oh. No, you have your.
Thank you very much. You are so nice, Sarah. And by the way, I'm the first among those people who are doing our work. So basically, in this talk, you can see essentially how we can connect causality with independence, and then how we can do adaptive prediction or transfer learning in a causal and non-causal way. Basically, I will start with this example. So in 2015, this system called photo categorization system developed by Google Photos made some huge mistakes, right? The system basically tagged 2 African Americans as gorillas, right? This is really a huge mistake. So they use deep learning. They really try to identify, to do classification. Why? What caused the problem? And after almost 3 years, 2.5, almost 3 years, finally they solved the problem. How did they solve it? Do you have a clue? How did they solve the problem? Sorry? Human label? Yeah, that's one way they didn't use it because they want to use the automatic system. To us, this is very simple. And finally, they solved the problem by removing the label. Yeah, you want to say that, right? So by removing the label from the label set, by removing gorilla label from the label set, you can see they spent very much time. They really want to solve the problem. The problem is very easy for us to solve, but for the computer, deep learning system is so hard. Why? And similarly, we know adversarial attack problem, right? So after you add some noise, all of a sudden, it's not a panda anymore, right? So what caused the problem? Basically, roughly speaking, this is just because the machines are using a different set of features than what we use, right? We use this kind of features. We derive the features in some way. Machines just use the features that are very useful for prediction implied by the training data. That's all. So basically, we use a different set of features. Now, we say we are intelligent. We want machine to be intelligent. What's intelligence? Traditional machine learning basically assumes that you have data, training data, and that the test data are from the same distribution, right? Basically, you have a single distribution. That's why you can learn something here and apply the same thing in the future. In practice, almost all the time, this is wrong, right? For us, for human beings, if you play badminton very well, you can easily learn to play ping pong, and you can quickly play it very well. You know how to decompose the whole skill set into some small modules, and you can automatically do the transfer. For human beings, right? For human driver, you can easily identify or make the right decision, even if this is a completely new scenario, because you can see the essential part of the input of the feature, and you can draw the connection between this kind of essential representation and your experience, something in your experience. We can do that. Overall, for a machine to be intelligent, we have to basically ask for the following things. First of all, the system should have the ability to understand what's going on. I'm not giving a definition of understanding. Later, I will try to do so. Basically, the machine has the ability to understand what's going on. And because of that, the machine is able to do control, intervention. The machine can automatically decompose a complex situation, complex task, into a lot of simple modules. And the machine can do information fusion. You mentioned fusion. Basically, you can just put together information or pictures you learn from different scenarios in different situations, and then you can form a bigger overall picture. And you can learn with few examples. In a new scenario, right? You can really see the connection between the scenario and the previous ones. Then you can do something with very few level data points. You can do not only interpolation, but also extrapolation, right? Even if the data point is not contained in the training set, you can really see the connection. You can make use of the connection. So we can do a lot of things. What is intelligence? We just talk about a lot of phenomena related to intelligence. How can we really achieve that? How can we define intelligence? Basically, what's intelligence? Some people may say, so, okay, I can see exactly how brain works, and then I can try to build something to mimic that. I don't think this is really the right way to achieve intelligence because there are so many ways, right? We just care about the input-output. We don't care about the particular detail in the system. Then how can you define intelligence? Basically, you can view this problem from the evolution, selection, and growth perspective. Now we want to define intelligence because we have those capacities. Now we want a machine to have the same capacities. What capacities? First of all, we survived, right? We survived different scenarios, meaning that we have the ability to make good prediction or good decisions across different scenarios, across all scenarios, right? Statistically speaking, this means we have to come up with some inner compact representation of the external world. You see different things. You really want to see, analyze, see, and encode the connection between different scenarios, between different tasks, and so on. So we can do this. Second of all, we are creative in some way. That's why we can create new things, and we are powerful, right? So creativity, clearly, to be creative, you have to make use of causal representations because you want to make intervention, you want to change something to achieve your goal. And we prosper, right? That's why we define intelligence. We want to do something, we want to develop something that behaves similar to us, right? So we prosper because we are creative and we survive. Now, we want to create some machine that has abilities. What can we do? First, let's notice the following thing. The two kinds of representations are somehow consistent. When we were very young as infants, we couldn't really do any intervention, right? We could just cry. We observe, right? We try to be secure. Basically, we try to make some prediction. We try to form some inner compact representation when we were very young. Later, we had the ability to make changes. We discovered a lot of causal relations. They seem to be consistent because there are no sudden big change between them. Now, given this, let's try to, and today I'm not going to talk about how to really achieve this, achieve a general purpose AI system. That's another story. But today, we want to have a look at the connection between you guys. We want to see.
Oh, we want to hear that story.
Yeah. After talk, let's talk. So basically, we want to see the connection between the two kinds of representations. And then we are going to answer the following three questions. First, we just analyze the data, observational data, and then the relationship of the representation is somehow consistent with the causal representation. How can we really analyze observational data to find the causal relations? This is the first issue, known as causal discovery. You'll see how we can solve the problem. The second one is, yes, the first representation is really useful for transfer learning or domain adaptation because with this, you can make very good predictions across all scenarios. That's basically transfer learning, right? Now you can see, oh, yes, clearly, the second issue is that how can we really make use of causal representations to improve our ability to do transfer learning, right? Suppose I know something about the causality in this system. How can we make use of it to do transfer learning? This is the second issue. The third issue is, yes, we can use causality. It's not necessary because not everything involved in this representation is causal, right? That means, yeah, probably we don't have, if we are giving data, only data, probably we don't have to go to the causal level. We can make use of something else, which is kind of similar to causality, to really do transfer learning. What's that, right? So you want to find an efficient way to encode the particular essential property of the data distribution to make to achieve transfer learning. What's that? So I'm going to focus on those three issues, and I will take questions during the talk. So if you have any questions, please let me know. we distinguish between causal connections and association information. This is the example, basically the news report from Telegraph. Couples who share housework are more likely to divorce. It's horrible, right? So we really want to see whether this is causal or just associational. That's why there was a lot of follow-up discussions. Does sharing housework really lead to divorce? We care about such questions because we want to see what we can do to improve your life, right? Association information, most of the time, doesn't really make sense. But for machines, that makes sense because they make prediction. This caricature, I think almost all of you right know this caricature, basically explains my experience. When I was very young, yes, if I see something with very strong, see very strong correlations or very strong dependency, yeah, there's a causality. There's some causal relation. Later, because of very famous claim or statement in statistics, causation implies correlation, but correlation doesn't imply causation, right? A lot of people just change their minds. However, after doing research in this field for, as you said, about 13 years, so now I'm very optimistic. Basically, I can say that in almost all situations, if you believe that the causal relations take place between given measured variables, then we can always discover causal direction and causal relations. However, this is the only part of the story. In a lot of situations, we don't have causality between observed variables. We have causality between hidden variables. We only observe a lot of reflections of those true underlying causal variables. This is much harder. And we are basically, a couple of people are currently doing this problem. Hopefully, within 5 years, you can see some very good solutions, maybe because of you. OK, what's causality? Basically, we say X will cause Y if intervention. If you basically, interventions on X can give you different values or different distribution of Y. Then when you do intervention, basically you only change the value of X. Everything else in the system, at least for the moment, is the same as before. That's why whenever you observe a change in the distribution of Y, you know, oh, this is because of the change intervention on X. That's why X causes Y. So clearly, if they are causally related, generally speaking, they are associated. They are associated only if they are dependent. It's much weaker. OK. In reality, in many situations, we really want to discover causal information from observational data. This is the particular example. So basically, this paper says large-scale psychological differences within China can be explained by rice versus wheat agriculture. So there are some explanations. I'm going to skip this. If you are really interested, you can read the paper. But basically, here you can see, in this kind of scenario, we cannot do intervention. Even if you are very powerful, you can force people, right, to farm different things. You have to wait really long to really see the effect, right? So we have to analyze data. We have to make use of statistical properties of data. This is another application, another example. Basically, my collaborator, Marlene Nobeck from the Netherlands. And her last name is very cool, Nobeck. Just go forward. So she collected 255 skeletons all over the world and measured 8 variables. They really want to see how those variables are causally related, because they really want to see why. Those features include sex, cranial size, right here, diet, what you eat, climate, cranial shape differentiation, basically what this part looks like. So they really want to see why people in different areas look different. They want to see why. And then they want to make prediction into the future, giving something that will happen in the future. So this is a very interesting problem, but you can see we cannot really do interventions. We have no choice but to analyze data. OK. You are going to see how we can make use of independence to solve this problem. But basically, we make use of independence, different levels of independence to find the causal structure. And then after that, you can see how we can do transfer learning also by making use of independence or some particular type of independent modularity. Basically, that's why independence is really essential property or essential concept in causality. How can we really discover causal information, causal structure from data, observational data? First of all, we know that if you have a causal structure, valid causal structure, we can see a set of independence and conditional independence relations. given by the Markov condition, called the Markov condition, right? If x equals y, if y equals x, and x equals z, in this way, suppose they are no compounder. Then we know y and z are conditionally independent of given x, because there are no other way for y to be related to z. Meaning that if I fix the value of x, then no matter how this guy changes, this one will not be changed by that. They are conditionally independent given the middle thing. Each variable is conditionally independent from its non-descendants given its parents. This is Markov condition. So from this condition, you can see, oh, we can see independence relations in the data if we are given the graph. Now we want to solve the inverse problem. We want to go from the independent property in the data, right, that can be discovered from data back to the causal graph. What can we do? If they are independent, basically, you can see the contrapositive of the Markov condition says that if they are dependent, then they are, rigorously speaking, they are deconnected. If they are dependent, then they are deconnected. This makes no sense, because we cannot really see any sparse graph if you make use of this property, right? We can only start with dependence to say to the conclusion that they are deconnected. But we really want to find a sparse graph to explain the data. What can you do? You have to make use of another assumption, which is known as faithfulness. This faithfulness is almost the same as faithfulness in the relations. It says all observed independence relations in the data can be seen from the graph by applying Markov condition. It means there are no fake or extra or spurious independence relations. Whenever you see independent relation in the data, right, it's a property of the graph. Then because of this assumption, we know, oh, there is some connection between causal graph and the statistical property of the data. Then, okay, from here, you can derive the following procedure. This is the PC algorithm to discover causal relations from data. We make use of conditional independent relations. And in particular, this set of methods is known as constraint-based method. Here, by constraint, I mean conditional independence or conditional independence constraints. So from data, you can discover a lot of constraints, independence, conditional independence relations. And then you want to find a DAG or a set of DAGs to satisfy those constraints. And you can show from the previous condition and assumption, you can show that, oh, if they are independent or conditionally independent, then clearly there are no edge between them. They are not adjacent. You can show this. Now we can say, oh, I started with this graph. I know 1, 3 are not adjacent. I know 1, 4 are not adjacent. I know 3 and 4 are not adjacent. You can directly see this from the graph. Oh, sorry, from the distributional information. Now, 1, 3 independent. This is the only way for them to be independent. Otherwise, right, you are going there. Otherwise, they must share information. They cannot be independent. So this is known as V structure. And then you can go further. This is not a V structure because they are not independent. They are independent given this guy, right? Clearly, this guy cannot go this way because if this guy goes this way, it means, oh, before you consider this guy, they are not related, right? After you consider this guy, they become dependent, which is different from what we observe from data. That's why this direction must go this way. This is called orientation propagation. You can find the V structure and the directions, and then you can go further by propagation. Okay, so here you can see a summary, very dense summary of the whole procedure. Basically, this method, PC or other constraint-based method for causal discovery, makes use of conditional independent relations. They rely on causal Markov condition and faithfulness assumption. And typical algorithm is the PC algorithm. P is for Peter Spertis, C is for Clark-Glimmer. And basically, there are 2 steps. First step is to determine the skeleton, undirected graph from the data. And the second step is to find the V structure and do orientation propagation. If all those DAGs discovered from data have the same direction everywhere, then it's just a DAG because all directions are consistent. Otherwise, if the same edge can have different directions across different solutions, then we just use an undirected graph, undirected edge right here. In this case, suppose this is the true ground truth. We know y is independent given x. All those 3 graphs will satisfy the same set of independent relations. Then we say, oh, basically, they are not adjacent, they are adjacent, they are adjacent. We cannot determine the direction because each of them can go in either way. Okay, this is known as a pattern or Markov equivalence class. So this is now we can see how this method works on this data set. We apply the PC method combined with our kernel-based conditional independent test method. This is the output of the method. A lot of edges are directed. Some of them are not, right? And if you further make use of some background information, you can go much further. This is the, so this is the location, basically. This is climate. Climate shouldn't be a cause of location, right? So I know, this guy should go this way. If this guy goes this way, this guy must go this way. Otherwise, you are going to have a fake V structure, okay? So all of a sudden, by making use of some background information, I have a DAG. And a lot of relations here, reported here, have been discussed in the literature. For instance, this one says climate causes the cranial size. You can see that in very cold places, usually people have a larger kind of cranial size. It's because if it's very cold, then it's better to warm the air for longer, right? Before you really exhaust the air. That's why these parts tend to be bigger. And so on. There are a lot of explanations in archaeology. Furthermore, from data, we recover not only those things, but with more details. So in the literature, they said, oh, diet is what you eat, basically, is the cause of a cranial shape differentiation. Essentially, what you eat will change your looks. From data, we say, yes, that's true. This is the cause. However, relative to this set of variables, this is not a direct cause. This causal influence takes place via another two variables. So from data, you can really discover more detailed or more complete causal picture. Yeah.
Sorry, what was the kernel-based conditional independence test? I'm curious why you had to innovate on the conditional independence testing framework.
So basically, this is just, what should I say?
Well, I'm just curious, like, what does that mean?
Oh, okay. So now I see. Basically, if you want to apply such method, you have to make use of independent conditional independent relations. You have to see whether variable are conditionally independent. So basically, this is just a non-parametric method for conditional independence test.
Okay, so that wasn't a contribution. It was just you had a non-parametric method that you found and then used it.
You're totally right. Yeah, it's just a kind of module. We just call the function. Yeah, wonderful. So now, so far, we haven't really seen anything about the confounder. By confounder, I mean a hidden direct cause of two variables, right? Hidden direct cause of two variables. And what if you have confounders? You only measure a finite number of variables. Can you really say anything about the confounders? This is really cool, because if you can say something about confounder, essentially you can say something universal regarding the universe, right? Given only a finite set of variables. The answer is yes. In a lot of situations, you can really say something about the confounders. Let's just have a look at two examples. In the first example, basically, this is a graph we just discovered. 1, 2 independent, 1, 4 independent giving 3, 2, 4 independent giving 3. Right? If you assume there are no confounders, this is the graph. Now the question is whether it's possible to have a confounder behind 3 and 4. Do you think it's possible at all to have a confounder there, given this set of independent relations? The answer is no. If you have a confounder here, then basically x1 and x4 will be deconnected given x3. This is not going to be the case. The same thing happened to the relationship between 2 and 4 given 3. So in this case, suppose the independent relations are really, really oracle. Basically, suppose we are very confident about that. Then we are very sure that there are no confounder between 3 and 4. And furthermore, we say x3 must be a direct cause of x4. So this is really informative, right? OK, now the scenario. You can look at the example later, OK? So suppose you observe the independence, those independent relations. 1, 3 independent, 1, 4 independent, 2, 3 independent. Of course, in reality, you can condition on some variable, doesn't matter. Basically, do you think there are confounders between 2 and 4? So this is the graph. 1, 3, not adjacent, because they are independent. 1, 4, not adjacent. 2, 3, not adjacent. 2, 4, not adjacent. This is the graph. So now you can see the following thing. 1, 4 independent. So if there are no confounder, then this guy must go this way. Otherwise, they share information, right? This guy must go this way. 2 and 3 are independent, meaning that this guy, this direction, this edge must go this way. You can see contradiction. Why do we have the contradiction? It's because of confounder. So in this case, we can conclude that there must be confounders between x2 and x4. And furthermore, you can say, definitely, there's no direct causal relation between x2 and x4. So in many situations, you can really say something about the confounders by making use of only conditional independence relations. Okay. Unfortunately, if you make use of conditional independent relations, most of the time, you cannot really uniquely identify the DEG because you have the equivalent class. You can only identify all the DEGs which have the same set of independent relations. Now let's try to go further. And here you can see some examples. We are given different data pairs. Each time we are given only 2 variables. We have no idea about the temporal information, so there are no temporal precedence information. We are given IID data. We are given, each time we are given x1, x2, a number of data points. And then we want to determine which one is the cause and which one is the effect. What can we do? Clearly, we cannot make use of conditional independent relations because we have only 2 variables, right? So now you can see, oh, you have to assume something slightly stronger. Then you can, all of a sudden, you can discover a lot of information regarding the process. Here you can see a number of functional classes. Basically, in the first one, the effective linear function of the cause is plus noise. This is the linear model. And we assume the noise term is non-Gaussian. Then this is the linear non-Gaussian model. And in the second case, the effective nonlinear function of the cause plus noise. The third case, you further have nonlinear distortion or measurement error, or measurement distortion in the data. Basically, if the true generating process, causal process, follows either of them, but this one is the most general one, follows this model, then in theory, you can show that the reverse direction, wrong direction, cannot give you independent noise. For the correct causal direction, we have independent noise. But for the wrong direction, you can never discover or estimate independent noise. This will give you asymmetry between the 2 variables. And that's why we can uniquely identify the causal direction. Here you can see some illustration. I generated x first, and then I generate y. So y is the effect of x with some noise, right? This is the functional form, causal process mechanism. First, let's consider joint Gaussian case. Right here, x is Gaussian, and E, the noise term is Gaussian. So basically, everything is Gaussian. All variables are jointly Gaussian in this case. I try to explain why the effect with the cause by linear regression. This is the residual. You can see the residual is uncorrelated from the cause, from the predictor, by construction. And in the Gaussian case, as long as they are uncorrelated, they are independent. The same thing happens in the reverse direction. I try to explain x, the cause, with the effect by linear regression. The residual is uncorrelated and hence independent from y. They are symmetric. X and y are symmetric. Cause, effect are symmetric. This is another scenario. Here, x is uniform. Noise is also uniform. Now you can see, oh, if I try to explain y with x, basically I just estimate, recover the underlying true causal mechanism. The residual is clearly independent from x because I use the independent residual. Here, the residual, if there are no confounder, then the noise term here must be independent from x. Otherwise, there must be confounder. There must be some other way for x, y to be related, meaning that there must be some confounder. That's why we can say if there are no confounder, then the noise must be independent from x, from the cause. And then let's try to explain the cause x from, by making use of the effect y. You do linear regression. Yes, the residual will be uncorrelated from the predictor by construction. Whenever you do regression, they are uncorrelated. However, as you can see from this scatter plot, clearly they are dependent. They are not independent. The distribution of the other variable will be very sensitive to the value of y, right? As you can see from this scatter plot. So this means, oh, generally speaking, this is just an example, but generally speaking, as long as at least one of them is non-Gaussian, then we can recover the causal direction because wrong causal direction will not give you independent error term, although the error term is uncorrelated from the predictors. And here you can see basically, I just talked about the variable case. You can handle a lot of variables. Here you can see some application in stock market analysis. Here, basically, we analyze the daily returns of a lot of stocks in Hong Kong stock market. Basically, all major relations are kind of consistent with the domain knowledge. Here, for instance, this guy this is the Hang Seng Bank. This is HSBC. HSBC holds something like 60% of Hang Seng Bank. Then you can see the causal relation from Hang Seng to HSBC, and so on. Okay, I'll skip this. Previously, we assumed everything was linear. Clearly, it's too strong, right? In reality, we really want to make use of a very flexible model to approximate the process. At the same time, we want to guarantee that even with this very flexible model, the causal direction is identifiable. The cause and the effect are not symmetric in terms of this model. So we came up with this model called the post-nonlinear model 13 years ago. Yeah, so basically, the effect is the nonlinear distorted version of the nonlinear function of the cause and the noise. This is very important because very often times we have sensor distortion, measurement distortion, right? Whenever you use an instrument to measure something, right? Very often times you have some additional distortion. So put them together, we have this model. We have two nonlinear functions. And you can see this model is rather general. For instance, even if the noise is multiplicative, not additive, you can see, oh, it's nothing but a special case of this model, right? So now, with this model, but we applied this model to the causality challenge, the second causality challenge. Basically, with this method, we correctly identified all causal directions. That's why this changed a lot of people's mind. Now you can see a particular data set. This is data set 8. We have data points. Right here you can see the data points. And we first assume x1 causes x2. We fit the model, estimate the nonlinear functions, and the noise. The noise is independent from the hypothetical cause. Then we assume x2 causes x1. We want to see which one is more plausible. And then we estimate the noise and nonlinear functions. You can see the noise is not independent from the hypothetical cause, which is x2. So basically, we say that causal direction should go from x1 to x2. Actually, x1 is the age of a lot of people, and x2 is the wage per hour. Clearly, x1 should cause x2, but not the other way around. Yeah.
Is this assuming no noise in the parents?
What? Say again?
Is this assuming no measurement noise in the parent variables?
This is perfect.
Is this assuming no noise in the parent variables? That was the question.
This is a wonderful question. Yes. And later you can see how you have to deal with the measurement error. Wonderful. You are totally right. Okay, otherwise, basically the true variable for the cause is the confounder. Yeah. Okay, so we can see, yes, empirically speaking, we can really discover causal direction and causal model from data, even if there are no temporal information. Right? We are giving ID data. So let me show some theory. Empirically, yes, it works, but can we really guarantee that? Essentially, we just tackled this problem with a proof of contradiction. We assume x1 causes x2. We have the data, then we have the distribution implied by the data. Now let's see whether the same distribution can be explained by the wrong causal model, wrong causal direction. How can we really solve the problem? We assume the same data can also be explained by wrong direction, which is from x2 to x1. Right? Now let's see in what situations this can be the case. After solving some equations, differential equations, you can see, oh, in only 5 situations, this is the case. Meaning that in only 5 situations, given data generated this way, the cause and the effect are symmetric because even for the wrong direction, you can find independent noise. But apart from those 5 situations, cause and effect are not symmetric. You can discover causal direction. Those 5 cases are very specific. The first one is the linear Gaussian case. Right? You already saw the picture. In the linear Gaussian case, basically causal direction, the information from causal direction just disappears. All of them are very specific. You have to tune the nonlinear functions and the distribution very carefully so that one of them holds true. Means that generally speaking, we can discover causal direction from data, even if the data were generated by this very general, very flexible model. By the way, it's very interesting to see why the linear Gaussian case, which is supposed to be very simple, right? Turned out to be so strange. In the linear Gaussian case, we cannot find the causal direction. Why? Because central limit theorem. If you have sum of independent variables, right, and if the number of independent variables is infinity, we have a Gaussian distribution, right? On the contrary, we have the Cramer decomposition theorem, which says that if the sum of any finite number of independent variables is Gaussian, then any of them, all of them are Gaussian. This means, oh, when I really discover or see Gaussian distribution, the process already converges, right? If the process converges, then the process information disappears. You only observe something that is fixed, right? But before that, you can always recover the process information, which is causal information from distributions. Okay, so now, first let's have a look at a lot of practical issues we have to deal with in causal discovery. Why do we have to deal with those situations? This is because we have to analyze the data. The data were generated by not only the causal process, but also how you measure the data, right? So you have to deal with nonlinearities. You have to deal with not only continuous variables, but also categorical variables and mixed cases. We have a lot of papers. Basically, we publish those papers to deal with those situations. You have to deal with memory error. The memory error is a really important issue. And we just published some papers on how to deal with memory errors in different situations. You have to deal with selection bias for causal discovery, because selection bias can change the dependency relation, dependent pattern in the data. Confounding is the most important thing in causal discovery. Here, I observe 1 and 2. However, there's a variable z as a direct common cause of them. Unfortunately, z is not observable. What can we do? Can we discover true causal relations? So basically, we are trying to solve this problem. We observe a lot of variables, xi's. They were generated by some hidden variables, and the hidden variables are causally related. You can consider those variables as concepts, right? You see a lot of images. Those images were generated by a lot of concepts. Those concepts are related, right? So how can you, this makes no sense, because what you observe is nothing but reflections of the underlying true causal variables. You have to go to this level to really make sense of the data. What can we do? Under what conditions can you really recover this kind of deep representation, graphical representation of the data? We call this confounding network discovery, because this is something like a confounding network. And also you can see the relationship between this and deep learning. This also explains why we have to use deep structures in a lot of scenarios. Okay. Missing values, you have to deal with missing values, because if you just ignore missing values, you can have extra or fake conditional dependency relation in the data. So we have some publications there. And causality in time series is a traditional problem. You have temporal information. However, if you really want to apply granular causality, right, to the data, in order for the discover the causal relation to be really causal, you have to make very strong assumptions. You assume there are no confounder. You assume you have the data recorded at the right frequency, right resolution, and so on. So to solve those problems, basically, we could estimate the time-delayed causal relations as well as the instantaneous causal relations or very fast causal relations. We can discover true causal relations from low-resolution data. Here, by low-resolution data, I mean you may have subsampled data or aggregated data, like daily returns. The daily return is nothing but the sum of a lot of local or short-term returns. So, and also, you have to deal with causal discovery from partially observed processes. Some of them, right, are not observable. How can you really recover the true causality between those observed variables? Basically, we made some progress in those lines of research. Furthermore, recommended systems. If you really want to design recommended system, you care about the causality, because you make this particular recommendation to change the behavior, right? If you just want to make a prediction, then this is nothing but recommendation for convenience. I know you want to buy this. That's why I recommend the same thing to you, right? But what you really want to do is to make changes, to change the user behavior. For instance, if you want to improve the revenue, maybe you want to find a way so that the user will buy more products in the long run. And if you want to make the world better, you want to find a way so that the user will be more fair, open-minded, and so on. So that means whenever you design any recommender system, you have to come up with some goal to achieve, and then you can make use of some causal inference techniques to achieve your goal. And then finally, non-stationary and heterogeneous data. We observe such data very often in reality. If you have time series, as time goes on, the distribution of the data can be different, can change. This is non-stationarity. If you have multiple data sets collected in different locations under different conditions, then the distribution can be very different. This is known as heterogeneous data. So how can we find the causality from such data? From the purely statistical perspective, non-stationary data is really, really horrible because I don't have a fixed distribution, right? However, from a causal perspective, we really enjoy analyzing non-stationary data because causality and non-stationarity or distribution shift are heavily coupled. We care about the causality because we want to make changes, right? In other words, causal model tells us how the distribution may change. To make it more specific, suppose X causes Y, raining causes wet ground. What do we mean by that? There's the process to generate X. There's another process to generate Y, the effect from X. The two processes are not related. They are separated. Meaning that, oh, I can have changes in Px, I can have changes in Py given X. They are not related, right? And we can easily discover and verify those conditions from non-stationary data. That's why, generally speaking, with non-stationary data, we can discover causal information more easily. Let's see how we can deal with the problem. Basically, we want to answer the following questions. How can we find where the mechanisms change? Meaning that we want to discover the variables for which the generating process changes. So we can do so. Suppose this is ground truth. From data, we know, oh, for V1, V2, and V4, the mechanism change. And furthermore, how can you discover the true causal skeleton? And the third problem is, how can you find the direction? In the non-stationarity case, it's really interesting that we can find the direction more easily because we can make use of independent changes in probability, distribution of the cause, and distribution of the effect given the cause because of modularity, right? We have separate independent modules. This is one module, this is another. They are not related. They are, if you have non-stationary data, we can say they change independently, although each of them is a high-dimensional object distribution. But we don't care. We can verify whether they are independent or not. So we can easily find the direction by making use of independent changes. And finally, we can also do some non-empirical method to estimate, to produce a low-dimensional representation of the non-stationarity. I know this causal relation, this causal mechanism changes. How can I really visualize how it changes? Basically, you just want to find a low-dimensional representation of the conditional distribution across different scenarios or over time. Okay, so let me say a few more words about independent changes. This is really a very nice thing if you have non-stationary or multiple domain data. Basically, independent changes between the cause distribution and the distribution of the effect given the cause. And this independence is generally violated in wrong causal directions. There are some special cases. I think you are familiar with some of them. In this case, we have invariant cause. Basically, C is a surrogate. If C points to this guy, we say, oh, this distribution, this mechanism, the mechanism for this guy changes. This guy is not adjacent to C. And furthermore, we know, oh, this guy is independent from C, given some other variables. Then we can say, basically, we have invariant cause. Vi is the invariant cause. That's why the direction goes from Vi to Vk. This is invariant cause. This is another scenario. Here, yeah, VL is independent from C, given some set of variables containing Vk. This is very different. Now you can see, although the distribution, marginal distribution of VL changes, however, the conditional distribution of VL given Vk will be the same. We say this is an invariant mechanism. Basically, if you have those invariance properties, you can discover causal relations. And the independent change is just a generalization of invariance. You can make use of that, and you can discover that. And here you can see, basically, you can discover causal relations by making use of changes. So here you can see application. We analyze the number of stocks, basically the daily returns of a lot of stocks in NYSE. You can find the skeleton or the direction, and you can see very nice patterns. Those companies in the same sector are closely related. Between different sectors, the causal relations are kind of more sparse, and basically we try to interpret the results here that seem to be consistent with the domain knowledge. And also, furthermore, we have the non-stationarity or visualization of the non-stationarity of the causal mechanism here. This is the USB, I forgot which one it is. Basically, this is how the causal mechanism to generate USB, stock return, daily return, changed over time. This is the 2008, this is 2007, financial crisis, right? You can see, oh, something's totally different from before. And actually, this line, this curve is very similar to the so-called curve of TED spread, TED spread, which provides a way to analyze the risk in the market, calculated in a very complex way. Basically, you can see this line is consistent with that. And furthermore, here in 2007, the risk is already very high. But in 2008, clearly the risk is even higher. Yeah.
So does your method need to identify different environments separately, or it can automatically figure out the non-stationary?
That's a wonderful question. You don't need to do that. You don't need to basically segment the data sets. You just need to, it's non-stationary, right? You can use something like a kernel method to make use of all data at the same time. Okay, finally, let me see how much time I have. Let me spend about 10 minutes on this part, transfer learning. Why do we need a causal model? First of all, if you want to make changes, if you want to intervene on something, or if you want to make proper changes to achieve your goal, clearly you want to make use of causal models, right? This is, I think all of us agree with that. In many situations, we don't really want to do intervention. We just want to make prediction, right? So in this sense, causal model provides a compact description of the properties of the joint distribution. Remember the example, raining wet ground, right? X causes Y. Then the two processes are not related. Basically, if you observe multiple realizations of the process, then the multiple distributions will follow some property given by the causal structure, by the causal model. Now, let's try to do the following thing. With the same causal process, we can observe a lot of distributions with different parameters or different causal models, right? So how can we jump from one particular distribution to another? Suppose here, right, we are familiar with this scenario. We know x, y value. We can predict y from x. In the next scenario, I just observe something. I want to predict y. I want to transfer information from this place to this place, to another place, right? What can we do? So first of all, if you have no idea about the relationship between them, then it's not possible to do proper transfer learning because you have no idea what to transfer. If they are arbitrarily different, you cannot do anything. And second of all, you can see causal structure is rather stable. We can make use of this. This is the bridge, right? I jump back to the bridge, then I can jump to another place by making use of a new proper parameter, right? So this is the transfer learning. Basically, we have data from some old data or source domain data in which we have both the values for the features and the value for the class label or regression target. We have x, y values. And in the future, we collect data, only the feature values, and then we want to make prediction. Clearly, the distribution can be very different. This is different from the classical setting in which the distribution is always fixed, right? You always have ID sampling from some distribution. Now we have different distributions. So we just want to jump from some places to some other place, and we know something can change. What can we do? First of all, I want to convince you that clearly, yeah?
Just to understand the setting of the previous slide, there are two things happening. One, the distribution is changing, and you are measuring different columns, because you just measure the X in the testing. You don't measure the Y there.
In the target domain, yeah.
Correct.
Yeah.
Okay, then two things. One, there is something happening between P1 and P2 that is changing, and the other one, you have different measurements. That's correct? This is the setting?
Yeah.
Okay.
So for classical transfer learning and domain adaptation, with a single source domain, you're right. In the target domain, we don't have y value. We want to estimate it. And a lot of people, including Sarah, basically focus on the multiple source domain scenario. You have multiple source domains in which you have both x and y. Now you have the same. Yeah, you are totally right. You are totally right. Okay. So let's just consider this example. Very simple example. Suppose this is me, right? You can see my figure, my shadow. Now, suppose I go to a new environment, completely new environment. First question, if you see my shadow, can you predict anything about my figure? Yeah. Can you? Yeah, okay. Why? It's because, oh, let's talk about why later. So this is the first one. Second, if you see my figure, can you see my shadow? Can you predict anything about my shadow? Do you know how long it is? Do you know where it is?
We see other shadows. We see
Yeah, that's true. You just see me. Suppose you just care about me. So can you really see anything? No, right? Why is that? And furthermore, what's the causal direction? This is because here, this is the cause, this is the effect, right? In our experience, daily life experience, we already learned a lot regarding this mapping, causal mechanism. We learned a lot constraints regarding the relationship between this guy and that guy, right? And then by making use of that constraint and some property here, we can recover this guy perfectly. Okay, this is because causality provides a set of constraints that you can make use of more intuitively. The effect contains the information of the cause as well as information from the environment, including where the light is from and so on, right? That's why with some constraints, you can separate the effect of the cause from the rest, meaning that you can recover the information of the cause from effect, even if the environment is non-stationary, right? In contrast, if you only look at the cause, there must be some information in the effect that cannot be explained by the cause, right? That's why without stronger assumptions, you cannot really predict effect from cause. But the prediction in the reverse direction would be much easier, generally speaking, if you have non-stationary environments, right? And here you can see basically we know causal direction and we know causal constraints. That's why we can do a lot of things. The idea is if y, the thing you want to predict is, yeah?
I was just going to point out that's a good example for, so not just transfer learning, but semi-supervised learning too.
You're totally right.
It's on the direction, yeah.
You're totally right. Okay, so fortunately, in classification as well as regression, in many situations, a lot of situations, y, the thing you want to predict, is actually the cause of what you see of the features. Right here, what digit you want to write down is the cause of the digit you actually have. Here, the disease, which you want to predict, right, is the cause of the symptoms, and so on. That's why you have this causal model. And you can have changes here, you can have change in the conditional distribution, and you can have change in both, in the distribution of y and the conditional distribution, or the mechanism. However, because of the previous intuition or illustration, we know as long as y causes x, we can solve this problem. We can do transfer learning fairly easily, even if we have no idea about the y value in the target domain. We are given only the feature values, right? We can do that. So you can see the method in quite some papers. Here you can see our application. Basically, it's a remote sensing image classification problem. We have a lot of remote sensing images, and we want to do classification. In total, we have 14 classes. We have 2 different areas. Now you can see you can do transfer learning from 1 to 2 and from 2 to 1. Basically, with this model, we can, the misclassification rate was reduced from 21% to 12% and from 26% to 14% in the 2 scenarios. You can really benefit a lot from the understanding of the underlying causal process. Here you can see another scenario. Essentially, still you can see y generates x, right? And we have some deep network to explain the generating process. In across domains, we have very low dimensional representation of the changes. That's why we can really see, between domains, we can see the change in the causal mechanism with this structure. We are given a source domain in which we have class label, and a target domain, we don't have class label, right? We do transfer learning by making use of this structure. And we have theta, one-dimensional theta, to explain why the distribution in the target domain is different from the distribution we have in the source domain. In the source domain, we found theta takes this value, and the target domain, the theta has this value. They are very different. That's why the two distributions are different. If theta value is the same, then distribution must be the same, because everything else is shared across different domains. Okay, what's more interesting is that follows. I use this structure, I can change theta value after I estimate the deep network, right? You can see what happens. I change theta value. Now I see, basically, we just learned that, it's only the change in the angle. You can discover that. And I think this is how we understand the difference across different scenarios. We want to find a compact representation of the difference, right? And then we make use of the difference, make a prediction. Okay. Now, let's consider another more general question. You can see that in transfer learning, causality really helps. If you know causal relations, and if you assume the data will generate a kind of perfect sample from the underlying causal model, yes, causality helps because causality provides some constraints, right? You can make use of. And you can further make use, if you have a causal structure, you can further make use of invariance in the relations, right? It's invariance-based prediction. Sarah did some very nice work in this line of research. Now, the question is, do we really need to use causality or causal picture for transfer learning, right? Probably we don't have to go that far. Essentially, we just we are given data. We just want to make use of the data to discover how the joint distribution changes. And then we want to make use of changes to predict, to produce optimal prediction. That's all. So this inspires the following way of following automated method for domain adaptation. We are given multiple domain data. From data, you want to find a graph or something to encode the changes. In particular here, if this guy has a theta variable, this means, this guy, the mechanism, the conditional distribution of this guy given its parents can be different across different scenarios. That's all. Those things are independent. We guarantee that. Those variables are independent. That's why we have independent changes between px1 and py given x1 different modules, right? We discover that from data by making use of causal discovery from non-stationary data or a lot of methods, right? However, we don't need to assume anything. We just discover the property of the data. It's not necessarily causal. And then, what's domain adaptation? Basically, in the target domain, we are giving information of the features. Given those values, it's nothing but inference of the y values on this graphical model, given the observed data for other features. So in this way, domain adaptation or transfer learning is nothing but inference on graphical models, right? You can discover everything from data. You make use of prior distribution, discover from data, and structure from data. You make use of target domain data, it's done. This graph is not necessarily causal, this graph. Let me just give a single example. So suppose this is the underlying true causal process, Y causes X, maybe disease, symptoms, clinics, right? We just assign patients to different clinics according to their symptoms. However, if you have data generated this way and apply causal discovery method or graphical model learning method from non-stationary data, you are going to learn this graph. Px can change, Py given X is always the same across the scenarios. Why? This is because Y is conditionally independent from S. Py given S is the same as Py given X and S. So Py given X is the same. This is what you discover from the data. Clearly, this is not causal, right? But this is a valid, compact representation of the change property of the data. That's enough. And then you can make use of this graphical model and observe the values in the target domain to make a prediction. And here you can see a simple application of the idea. Basically, suppose this is here we have someone, we want to predict the location from the Wi-Fi signal strength is, we have a lot of routers, and right here, he or she can receive signals from different routers, and from the strengths of the signal, we want to predict the location of the person. That's the setup. So we can do this. We can measure the signal. We can measure everything from different time periods, and then we can do transfer learning. Say we can use a signal that we recorded in the morning and noon to predict something that is happening in the evening. So we want to transfer learning. This is, first of all, from data. We have multiple domains. We have data, signal strengths. We have wide location. We can first construct the graph to encode the distribution property of the data. And then by making use of this graph and the target domain data, we can make a prediction. So here you can see the result accuracy given by different methods. This is by domain invariant component analysis. So basically it's 29%. And with this method, automatic way of transfer learning is 64%. You can really see a big gap between the result given by this method, automated approach, and other approaches. Because here we can really somehow optimally make use of the property of the data, changing property of the data. Of course, the prediction should be more flexible, and at the same time, you don't assume anything that is fake. That's why the result is clearly superior to other results. Okay, to summarize, we care about the causality. Even in machine learning, right? If you want to deal with the problem of adversarial attack, you really have to find a way to derive the features we are using to do classification. Otherwise, if you know the features the machines are using are different from our features, clearly you can always do something like attack. And we can discover causal information from data by making use of different kinds of independence relations. With conditional independence, we can find a skeleton and some directions, which which is known as the Markov equivalent class. With independent noise condition, in some constrained functional causal model, we can discover causal direction. We can discover the whole DAG uniquely. Furthermore, if you have non-stationary or multiple domain data, you can make use of independent changes in the causal modules. This way, you can discover direction as well as skeleton more easily. And also, if you want to do transfer learning, essentially, you want to make use of a compact representation of the changes in the distribution, right? The more compact the model is, the better the prediction will be, because you have fewer changing variables, right? You have fewer parameters to estimate. And here, modularity implied by causality clearly matters. If you have causality, causality implies modularity. And if you further assume what you observe is a perfect sample of the causal model, then you can do transfer learning. Otherwise, if you just observe data, you can just make use of some graphical model to encode the independent changing property of the data. And then domain adaptation is nothing but inference on graphical models. Thank you very much. Basically, a lot of collaborators, so I cannot acknowledge all of them one by one, but basically listed here.
So, questions?
So specifically with regards to non-stationarity and let's say domain adaptation, many of the settings that I think about, the underlying causal model is not really on the variables that I observe, but rather on some hidden process. How would you think through applying these types of techniques in that setting?
Wonderful. Look at this picture. Here you can see we have theta. Theta is the latent variable. You want to observe the generating process. You want to explain how the observed features were generated by making use of some hidden variable. You can think of theta I as a confounder. Yeah, you can do this and in a non-parametric way. Because in theory, you can prove the identifiability of the conditional distribution by making use of a non-parametric model for the generating process. Essentially, I can put it this way. You want to see y, suppose y generates x. You want to see y and how px given y, the generating process, changes across domains. And you want to encode such information in a very compact way. you can achieve that by making use of some structure like this. Is that the answer to your question?
Any other question? Also on the other side of the room, by the way, if by chance anybody has any question. Okay.
So you said if you encode the changes in different environments appropriately in a graphical model, although it is not causal, that is still sufficient because the rest of the problem is just inference on a graphical model.
Exactly.
I mean, I don't exactly understand what you mean by just an inference on this graphical model, because if I do not know in the target domain where my changes are going to be, how can you get the causality stuff wrong, but just still have a graphical model, but then still generalize?
Okay, very good one. So whenever you do learning, you have to assume something. Even if you do regression, right, you assume the future data points will follow the same distribution. That's why you can guarantee that the learned model will have some capacity in the future, right? The same thing happened here. Basically, whenever you discover this model is an induction problem, you have to, where is it? The assumption that follows, you have a mother distribution, a hyper distribution regarding all variables to generate different distributions, right? And then you want to recover the property of the mother or hyper distribution represented by the graphical model, right? And in this representation, you have structure, you also have the prior distribution of the theta variables, then basically you specify everything. Now, in the new domain, target domain, you observe a set of values for those features. You are given structure, you are given prior distribution, you are given observed values for some variables, you do inference. Does that answer to your question?
Yeah, but I have a little bit of difficulty because you impose a prior on the thetas.
You learn that from software.
Yeah, you learn from you learn that from the data that you have already observed. With respect to that prior, you're just saying do an inference on the graphical model.
Yeah, to the right.
And you should be okay.
Yeah, to the right.
So maybe one last question, and then we should probably go to the poster session. Anybody? No, everybody's shy. Oh no. Okay, Kartike has several questions.
Wow, you already have.
Okay, so there is some recent work on invariant risk minimization, which also seems to attack the same problem that you're talking about. The causal graph is completely hidden, and you have a projection, like in the form of an image that I see.
Yeah.
And what they advocate is, I mean, there's a criterion, right? So I just want to know your comments. Is like, how is that?
Very good one. Very good one. So basically, I would say invariance-based prediction is a special case. You know all of this part is invariant, then I can make use of this relationship for prediction. However, this is far from optimal prediction, because even if everything changes, we human beings can still make prediction. It's about how certain you are about that prediction, right? So ideally, you have to make use of not only invariance properties, but also everything that is informative right here, right? So that's why basically with the inference on graphical model, you have posterior, you have certainty, right? So the point is, even if everything changes, you can still make non-trivial prediction. And in order to make optimal prediction, you have to find a way to incorporate such information. That's why it's more general.
Okay, just about the setting. Are you assuming that you are measuring everything in the target as well?
Say again?
Are you I'm trying to understand your setting here. What are the constraints and so on? Are you assuming that, in the same way that I asked before, are you assuming that you measure all variables in the target, or you don't measure y as well, or something?
You don't measure y in the target.
Okay, that's okay.
That's why you want to infer the y value from x values.
So it's unsupervised multi-source domain adaptation.
Data there?
No, you have finite data, yeah.
Okay, so maybe we can still thank Koen again.
Thank you very much.